Have you ever really thought about how mapping apps work? Like, down to the details. They guide us around, show traffic, sometimes even suggest parking.
hmm
But picture mapping every single potential parking spot on every street, manually. It seems, well, almost impossible, doesn't it? How do they manage that, especially without someone literally drawing every single line?
It is a massive challenge, you're right. Trying to hand label every curb for parking. It'd be incredibly expensive, take forever, and probably be out of date almost immediately.
Yeah, things change so fast.
Exactly. And that's where projects like Streetlines come in. They're really quite clever. They're designed to sort of infer where road lines and potential parking spots might be.
Infer, so like guessing based on the road.
Pretty much.
Mm-hmm.
Approximating the street geometry and where parking could fit. But without needing those giant perfect data sets like OpenStreetMap for every single detail, it's about getting a practical, usable result without mapping the whole world by hand.
Okay, let's dig into that. So our mission for this deep dive is to really unpack the core of the Streetlines tool, the actual math algorithm it uses to draw those parking rectangles.
Right.
And what sounds really interesting is how it deals with the whole Earth is round problem when drawing on a flat map or screen. Because, yeah, the Earth definitely isn't flat.
And that's the fascinating part, mathematically speaking.
Yeah.
How the algorithm manages to get decent accuracy by cleverly switching between different ways of looking at the world, different coordinate systems. It's a classic problem in geospatial stuff.
Yeah.
You can't just project a sphere onto a flat surface without some kind of distortion or approximation.
Right. So let's set the scene for how it calculates things. Let's say you've got a piece of a street, maybe the middle of a block. You know its center point and roughly which way it's heading.
Okay.
The goal is to draw two parking rectangles, one on each side, lined up perfectly with the street. And they need to be specific sizes, length, width, and how far they are from the center line. Sounds simple enough on the surface.
That's the objective, yes. But the core difficulty, like you said, is we're starting with latitude and longitude on a round Earth.
Yeah.
You can't just add, say, 5 meters to a longitude value and expect it to be exactly 5 meters on the ground everywhere. It doesn't work linearly like that because of the curvature, especially over larger distances.
Okay, so how does the algorithm handle that? Does it just kind of ignore the curve to start with?
It does something quite neat. Its first big move is to create, let's call it a temporary flat Earth playground.
Ah, okay. A flat Earth playground.
Technically, it's called a local Cartesian coordinate system, specifically east-north up, or ENU. Imagine you just take that street center point, it's Vlat and Vlon, and make that the 0, 0 origin of a tiny temporary flat plane.
Ah, I see.
And on this plane, east is your x-axis, north is your y-axis. It makes the local math much, much simpler for that small patch.
Gotcha. So for that little zone around the street center, you can just measure things directly in meters, like on graph paper. What information does the algorithm need to, set up this playground and know what to draw?
Right, it needs 3 key pieces of input for this local stage.
Okay.
First, the street center point itself,
Mhm.
that Vlat-Vlon pair in decimal degrees.
Yeah.
Second, the street orientation, which is an angle, date, theta, usually in radians, measured clockwise from true north. That tells it which way the street is pointing.
Makes sense.
And third, the rectangle dimensions, called B.
Uh-huh.
But B is actually 3 values bundled together, K, H, and W.
K, H, and W. Let me guess. H is height or length. W is width. What's K?
You got H and W, right? H is the height along the street, so the parking spot's length. And W is the width perpendicular to the street. K is the interesting one. It's the perpendicular distance from the street's center line to the closer edge of the rectangle. It's the offset.
Ah, the offset. So you're telling it, okay, here's the street center. It points this way. And I want a parking spot that's, say, 5 meters long, H, 2.5 meters wide, W, and starts 2 meters out from the center line, K.
Precisely. That's exactly it. Those parameters define the whole shape and position within that simplified local system.
Yeah.
And that K value is really important. Make sure the parking spot is offset from the middle of the street, where cars are supposed to drive.
Right. That would be bad. Okay, so we've got the flat playground set up. We know the dimensions. How does it actually draw the rectangle shape? It needs coordinates, right?
It does. It starts with a kind of blueprint, a standard shape. That's the vertex template matrix, M. This matrix just defines the 4 corners of a basic rectangle relative to the origin,
Yeah.
0, 0 of our flat playground.
Like standard corner points.
Yeah, based on the dimensions you provided. So the corners might be at coordinates like W2, K, W, K plus H, W2, K plus H, and W2. See how W determines the width around the y-axis, and K and H determine the position of length on the y-axis? That K value directly sets how far the bottom edge is offset from the origin, our street center line.
Okay, that makes sense. It's a standard rectangle sitting there at the origin, offset by K. But streets aren't always pointing straight north, right? How does it line it up with the actual street direction, that Fay angle?
Good question. That's the next step. Rotation. We take that basic template rectangle we just made and rotate it. We use a standard mathematical tool, the rotation transform matrix.
Okay.
This matrix just spins the rectangle's coordinates counterclockwise by that street orientation angle
Right.
within our flat plane. The output is, let's call it rotated the same 4 corner points, but now they're pointing in the same direction as the street.
All right, so now we have one parking spot correctly oriented on one side of the street center line in our flat playground. What about the other side? Does it have to do the whole template and rotate thing all over again?
This is where it gets really efficient and honestly quite elegant. No, it doesn't repeat the whole process. Instead of recalculating everything for the second spot, it uses a brilliant shortcut. It takes the coordinates of the first rectangle, one that's already rotated, and it just mirrors them across the origin.
Mirrors them? How?
Mathematically, it's super simple. It just multiplies the rotated coordinates by -1. That's the same as a 180-degree rotation. It does this before converting back to real-world coordinates. This guarantees the second rectangle is perfectly symmetrical to the first one, right across the street center line.
Wow, okay, that is clever. It's like a digital mirror image.
Exactly. It highlights something important, too. The rotation matrix preserves the shape and angles, and then the 180-degree flip ensures perfect symmetry. It saves a ton of calculation. Why do the work twice when you can just flip it right?
Totally. It's like photocopying the first parking spot and just turning it around. Okay, I love that efficiency. So now we have these two sets of coordinates, one for each side of the street, rotated, mirrored, but they're still in meters in this temporary flat world.
Correct. Still in the ENU playground.
How do we get them out of the playground and onto the real curved Earth map with actual latitude and longitude?
That's the crucial translation step back to reality. We need to convert those meter-based coordinates back into degrees of latitude and longitude. This is done using another matrix, the geographic normalization matrix. Let's call it G.
Geographic normalization matrix, G. What does that do?
Think of G as the reality check matrix. It basically uses scaling factors that tell us, okay, at this specific latitude on Earth, how many meters correspond to 1 degree of longitude change, and how many meters correspond to 1 degree of latitude change.
Because that changes depending on where you are on the globe, right?
Precisely. Lines of longitude squeeze together near the poles, so a degree of longitude covers fewer meters there than at the equator. Latitude changes are more consistent, but still depend on the Earth not being a perfect sphere.
So G needs to know the latitude.
Yes, it uses VLAT, the latitude of our street center point, and it relies on an accurate model of the Earth's shape, like the WGS-84 ellipsoid, to get these conversion factors, GLAT and GLON, right. That cos-VLAT term you often see in these calculations. It's vital for getting the longitude conversion correct, adjusting for that pole squeezing effect.
Okay, so G applies these scaling factors, converting the meter offsets into degree offsets. But the coordinates are still relative to where we started, that temporary origin point, right?
Exactly. They're now in degrees, but they're still centered around zero in our local system. The very last step is simple addition.
Just add the original coordinates back.
Yep. You take the calculated degree offsets for each corner point after rotation, mirroring, and normalization, and simply add the original street center coordinates, VLAT, VLON, to them. That effectively picks up the rectangles from the flat playground and places them correctly onto the global map. And voila, you have your 2 parking rectangles, R, ORO, and R, positioned in the real world.
Yet that whole process, wow. It's intricate, but sounds very logical, setting up a simple space, doing the geometry, then carefully translating back. But you mentioned approximations. There has to be a catch with that flat Earth playground idea, right?
There is, and it's important to be aware of it. The main limitation, the fundamental simplification here, is that planar approximation. We pretended a small patch of the curved Earth was flat for calculations.
And it's not perfectly flat.
It's not. So doing that will introduce some amount of error. It's an inherent trade-off you make for the simplicity and speed of the calculation in that ENU system.
How big is this error we're talking about? Is it like meters off or just tiny amounts?
For relatively small areas, close to the center point V, the error is usually quite small. The documentation suggests typically less than 0.2 meters, so maybe, 8 inches or so, for distances under 50 meters away from that center point.
Okay, 50 meters, like
Yeah.
half a city block, maybe? Less than a foot of error sounds pretty acceptable for estimating parking.
For many applications, it is. But the key thing is that the error grows significantly as you get further away from that center point V.
How does it grow? Linearly.
No, it's worse than linear. The error is approximately proportional to the square of the distance, d, from the center point. The formula is roughly E2, 2, Ruth, where Ruth is the Earth's radius.
V squared. Okay, so double the distance, 4 times the error, triple the distance, 9 times the error. That could get bad quickly on a long street.
It can add up, yes. And there's another factor, latitude. The error also tends to increase at higher latitudes, closer to the poles. Because those lines of longitude, the meridians, converge much more sharply near the poles. The flat plane assumption just becomes less accurate the more curved the actual grid lines are in reality.
So it's like using a flat map to walk around your local park. Probably fine, no big deal. But trying to use that same flat map logic to navigate across the entire country, you're going to have problems.
That's a perfect analogy. It really forces you to think about the scale of your application. How much error can you tolerate? If you need centimeter precision a kilometer away from your starting point, this simple method isn't enough on its own. Understanding that D2 error growth and the latitude effect is crucial for using this algorithm responsibly.
It's that classic engineering trade-off, isn't it? Speed and simplicity versus absolute precision.
Exactly. It's about finding the right balance for the job. And the beauty here is that the error characteristics are understood. It's not just a black box. We know why and how much error is introduced.
Which is really valuable. Okay, so if you do have a very long street or you need higher accuracy further out, are there ways to, work around this limitation?
Yes, definitely. The documentation suggests a couple of smart strategies. The most obvious one for long streets is segmentation.
Just chop the street into smaller pieces.
Right. Break the long street into, say, 50-meter segment. Then apply the algorithm independently to the center point of each small segment. That keeps the distance d small within each calculation, minimizing that D2 error accumulation.
Makes sense. Treat it as a series of short streets instead of one long one. Any other tricks?
Another approach is iterative refinement. You can use this algorithm to get a quick, approximate result, your first guess, for the parking spots. Then you can use that guess as a starting point for more complex and computationally heavier geodetic calculations that do properly account for the Earth's curvature to refine the position.
Ah, okay. So quick and dirty first pass, then follow up with the precise tools if needed.
Exactly. Use the fast method to get you in the ballpark, then refine.
Got it. So beyond the accuracy limitations, are there other sort of practical things to watch out for when actually implementing this, like coding it up?
Yeah, a few things. Numerical stability is one. You probably don't want your H and W values, the height and width, to be incredibly tiny, like millimeters, as that might lead to floating point issues in the math.
Right. Computational fuzziness.
And the geographic limitations we talked about, it's designed primarily for mid-latitudes. Near the poles, the geometry gets really weird, and this algorithm might give unpredictable results. You'd likely need special handling for polar regions.
Okay.
And, maybe the most obvious one, data quality. The output is only as good as the input. If your initial street center point or the orientation angle is wrong, your parking rectangles will be in the wrong place or pointing the wrong way. Garbage in, garbage out.
Always the case with data.
And finally, using accurate constants is important. Getting the values for the Earth's radii of curvature right, usually from that WGS84 model, affects the precision of the meter to degree conversion. Little details, but they add up.
So, assuming you've coded it carefully, used good input data, how do you actually check if it's working correctly? How do you validate the output?
Validation is key, absolutely. There are several ways. The simplest is often visual inspection.
Just look at it on a map.
Yeah, plot the generated rectangles on top of satellite imagery or a base map. Do they look right? Do they line up with where parking seems to be? It's a good first sanity check.
Okay, what else?
You can do numerical verification. If you have a few known correct coordinates for parking spots, maybe from a precise survey, you can compare the algorithm's calculated coordinates against those known values.
See how close it gets.
Exactly. Then there's unit testing, which is crucial for software development. You create automated tests that feed the algorithm various inputs, normal cases, edge cases like streets pointing exactly north or east, maybe 0 dimensions, and check if the output is mathematically correct or handles errors gracefully.
Testing the boundaries.
Right. And the gold standard, if you can get it, is comparison with ground truth. If actual detailed measurements of parking spaces exist for an area, Comparing the algorithm's output to that real-world data is the best way to assess its accuracy in practice.
Okay, so stepping back a bit, we've gone through the clever math, the approximations, the limitations. What does this all really mean? Why should someone listening care about this parking rectangle algorithm?
Well, I think it connects to a bigger picture about how we can use computation to understand our world, even with incomplete data. This algorithm, within the Streetlines project, shows the power of computational geometry. It lets us infer useful information like potential parking availability from relatively sparse input, just basic street center lines and orientations.
So it helps fill in the gaps in our maps.
In a way, yes. It allows developers or urban planners or researchers to get insights into city layouts and potential infrastructure, like parking, even in places where highly detailed, expensive map data doesn't exist or isn't accessible. It transforms basic street data into something more actionable.
So even without a perfect map, this algorithm gives you a pretty good guess at where parking might be, all thanks to some smart geometry and careful approximations.
That's a great summary. It provides a robust, well-documented method to get those reasonable estimates efficiently. It's about making the most of the data we do have.
So we've journeyed from just thinking about a parking spot through this idea of a flat earth playground, rotations, mirroring, and back to the real curved world on a map. It's amazing how much complexity is hidden in generating something that looks relatively simple on our screens.
It really is. It shows the ingenuity involved in bridging the gap between the messy, curved reality and the neat, flat representations we use in computers. Using that local ENU system is a classic, elegant way to handle these kinds of geospatial calculations.
This whole deep dive definitely highlights how these seemingly straightforward digital tools we use every day often rely on layers upon layers of clever algorithms and mathematical tricks.
Absolutely. Balancing that simplicity for calculation speed with enough precision to be genuinely useful is a constant challenge in computing.
It really makes you stop and think, doesn't it? What other complex real-world things are being simplified, approximated, and transformed by algorithms running behind the scenes just to make our digital lives run smoothly?